All right, so let's look. All right, looking at our worksheet, any particular problem you want me to help you with? You want to do the elevator problem, or do you want to move on to question number 2? Can y'all do the elevator problem? All right, let's look at the elevator problem. All right, number 1. All right, so we've got a fish weighs 10 newtons at rest, okay? When it is weighed on a spring scale in an elevator accelerating upwards at 2 meters per second, the scale will read what? Okay, well, we always draw it. Oops. All right, we draw it. Man, that's horrible. Let's try it one more time. Cable. Close enough. All right, then we got a scale here. And then we got a fish. Boy, I'm telling you, that's a fish, isn't it? Okay, do like this. There we go. All right. Okay. And somebody was saying, what on God's earth is a fish doing hanging in an elevator? I don't know. All right. Okay. All right, so we draw it. Now, let's determine what? Notice it says that the elevator is accelerating at what? 2.6. Whoops. Wrong way. The elevator is doing what? It is accelerating upwards at 2.6 meters per second squared, right? Okay. All right, now, let's determine now, we've drawn it. We've not finished labeling it. We'll do that in a second. What scenario applies here? The sum of the forces, remember I said you have to do this before you do anything. The sum of the forces is what? Is it equal to 0? Or is it equal to MA? Very good, it's MA. And how do you know that? Because it told us it is accelerating. The elevator is accelerating, okay? Now, let's draw our coordinates. So we've drawn it, we've labeled it. Let's draw our XY axis. I'm going to do them right there. If you want to do a dotted line, you can. Y and X, okay? You can do it like that, okay? All right, a couple other things. Notice it says that the weight of the fish is equal to what? 10 newtons? Okay. Which way is the force of weight? Force of gravity? It's down, isn't it? mg, which is this right here, right? All right. One other force we've left off. Let me ask you something. Is there any tension in that elevator cable? You better hope and pray to God there is if you're in it. Because if you get on the elevator and there's no tension, guess what? Bye-bye. You will hit the bottom at a very high rate of speed if the brakes don't stop you, the safety brakes. Which all of them have that now, but yeah, I guess you could disable them. So we got tension. And tension is which way? Y'all, it's always got to be up. Okay? All right? All right, now we got to write an equation, y'all. We got to write an equation. Notice we got our XY coordinates. All right, notice tension is up, so tension is positive, isn't it? All right, which way is mg? Well, here's your coordinates right here. Notice mg is what? Right? And it's equal to what? Well, it was accelerating, wasn't it? Okay. Now, we're not taking into consideration the weight of the elevator and all that. We're just setting that aside. We just want to know how much the scale will read. Well, look, y'all, the cable is hooked to the elevator and the scale is hooked to the top of the elevator. And so my tension is going to be, because you said, wait a minute, what about the weight of an elevator? Well, yes, it would be, but we're taking that out. All we're looking at is the scale. Okay? In other words, we're just assuming that this cable is hooked straight to the scale, which in a sense it really is. The cable's hooked to the top of the elevator's hooked to the scale. So in a sense it really is. So we want to write our final equation as to what? T is equal to mg plus ma. All right? Now, we didn't find the mass of the fish, did we? Well, look, y'all, we know weight's equal to mg. You know this. So the mass of the fish is equal to the weight over g. So 10 newtons divided by what? 9.8 meters per second squared. And the mass of the fish is equal to 1.02 kilograms, correct? All right, now, so let's solve. All right, so tension is equal to what? Looky here, both of these masses are the same, so we can factor them out. So we got 1.02 kilograms. And acceleration, so we got g, 9.8 meters per second squared. Thought it was negative. It is right there. Look, right there it was negative. But remember, we solve for t. We do what to the mg? We add a mg to both sides. All right. All right. Plus, I don't know why I'm doing that, but I'm doing it. Put in parentheses what I'm talking about. And so you should get an answer of 12.65 newtons, correct? Everybody agree? All right. Easy problem. By the way, I like elevator problems. Okay. All right. All right. You want to look at number 2? Oh, me, Mr. Shields. How do we do that? I don't know. Let's see how we do it. All right. No, I do. No, I'm just kidding. All right. So let's draw it. And it's hard. I drew that too long. All right, that's supposed to be a 90-degree angle. Why do I have a hard time drawing 90-degree angles? Okay, 90 degrees, close enough. All right, so this is 90 degrees. This side is 5 meters. This side is what? 4 meters. This side is 3 meters. All right, okay. All right. Now, we've got a box hanging here, and it has a weight of 4,500 newtons. Okay. All right. Are you watching? All right. Now, so it says we got a cable system hanging from a beam is configured as shown in diagram below. 4,500 newton weight hangs from the cables. What is the tension in cable 3? I'm going to label this T1. I'm going to label this T2, and I'm going to label that right there T3. Is that okay? Can we do that? That's really how you need to label them too. All right? Okay. So we've drawn it, we've labeled it, free-bodied it. We know that this is pulling downward, isn't it? mg, right? And mg is that right there, right? Correct? All right, now, do we need to draw our coordinate system? You better believe it. It actually makes that sound when you do it, okay? All right, now. All right? All right, we're still missing a few other things. We got to find, we don't have no angles. Well, we have one. Well, it gives us the dimensions. All right, precious children, can we not use trig and find that this angle is 36.9 degrees and this angle right here is 53.1 degrees? We can use trig. Now, y'all, I'm not going to do that. You can do it. You know your trig functions. SOHCAHTOA, all right? Just remember SOHCAHTOA. All right, now, okay. All right, we're doing pretty good. All right, now, let's label our angles. We'll get to a formula here in a minute. Let's label our angles. What is this angle right here? Remember, we always do it counterclockwise from the positive x-axis. All right, if this angle is 36.9 degrees, and guess what? That angle is 36.9 degrees. How do you know that? Geometry. All right. Okay. Now we got to label this angle right here. All right? We'll call this theta 1. We'll call this theta 2 if you want to. All right? Or theta, actually I probably should say theta T1 and theta, anyway, doesn't matter how you label them. All right, well look, if this angle right here is 53.1, then that means this angle right here is 53.1. But I want to know what it is from 90. So 53.1 minus 90, minus 180 is what? 126.9. So that angle right here is 126.9 degrees. Do you see how I got that? If this angle is 53.1, this angle is 53.1, well, 180 degrees is from here to here. Well, I'm here. So 180 minus 53.1 is 126.9, right? Okay. One more angle. Because, see, we have 3 tensions. What about the angle right here? Theta 3 is 270 degrees. Okay. All right. You ready? Okay. Okay, all right, now we've done all our labeling. We have not determined, though, is this object accelerating? Is it at equilibrium or is it accelerating? It's hanging there. It is at equilibrium. So what do we need to write for our sum of the forces? Sum of the forces is equal to 0. Very important. All right, now. Okay. Okay. All right. Notice we have components. Notice that these vectors are at angles. Oh, me. So what do we got to do? We got to write an equation for the sum of the forces in the x direction. Well, how do we do that? Well, we do it just like this right here. All right. So we say the sum of the forces is equal to what? Well, the sum of the forces in the x direction is T1 cosine of what? 129.6? 26.9, plus T2, here's T2 cosine of what? 36.9 degrees, right? All right, now what about T3 in the x direction? Plus, all right, what is the cosine of 270? Let me go ahead and write it out. 4,500 newtons. See, it already gave us that one. Cosine of 270 is what? Is 0, isn't it? And it's equal to what? All of that equation is equal to what? 0. Now let's do the sum of the forces in the y direction. See, we've got 3 forces, but 2 of them are unknown. Uh-oh. When you have 2 unknowns, what does that usually mean? One of 2 things you got to do. You got to either solve with the matrix, do a determinant with the determinant method, or simultaneous equation, right? And since y'all have not had linear algebra, we're not going to do the matrix, okay? But you could do it with that because why? Because it's a linear relationship. The force is proportional to acceleration. Directly proportional. All right, it's linear. All right, so what are the sum of the forces in the y? Well, T1 sine of 126.9 degrees plus T2 sine of 36.9 degrees plus, all right, now, what is 4,500 sine of 270? It's -1, so it's negative 4,500, isn't it? Okay, so this right here is 0, and this right here is negative 4,500, isn't it? All right. Oh, me, teach. We've got 3 variables and 2 unknowns. I'm going to cry. No, you're not. You're going to do a simultaneous equation. All right? Okay. All right. Now, there's something we should note, too, here about our vectors in the x direction. They will cancel each other out. Now, if you'll do the math, you will see that. You say, well, are we not going to have to solve for the forces? Nope, they will cancel each other out. All the force is in the y direction. It's pulling straight down. Okay. All right. They will. You can go and do it. Just trust me. They cancel each other out. All right. All right. So now what do? Well, I tell you what. We're trying to solve for what? What is it at? What does it tell you? Solve for the 3-meter cable. So we got to solve for T1, don't we? Question mark? Okay. Well, let me ask you this. Could I come to my f equation, my f of x equation right here, solve for T2, and then substitute for T2 to get T1? Could I do that? Could I? Because look, what does this equation look like? All right, let's do this. Let's go ahead and work it out. What is T1 cosine of 126.9? All right. It's negative 0.6 T1, right? And what is cosine of T2 cosine 36.9? It is 0. What? 799 T2, right? What is the sine component? T1 is, well, let's write the opposite, isn't it? Right? Yeah? All right, now watch. Go back to this equation. Go back to that equation right there. So we've got negative 0.6 T1 plus 0.799 T2 is equal to 0. And we're looking for T1, but how am I going to get T1? I got to solve for T2. Well, how do I solve for T2? You add a positive 0.6 T1 to both sides. Right? Okay. And what does it become? It becomes 0.799 T2 is equal to 0.6 T1. T2 is equal to what? 0.6 T1 divided by 0.799 T. Wait a minute. Look, no. I'm getting ahead of myself. Sorry. There we go. Right? Now, what is T2? Well, 0.6 divided by that is what? 0.75 T1? Right? Does everybody agree? So T2 is equal to 0.75 T1. Right? Okay. All right, now let's go back and take this equation, the whole thing, and substitute in where we see T2. You ready? You ready? All right, so the sum of the forces into Y is equal to, was it 0.6 times, what was T2? 0.75 T1, right? Plus 0.799 T1. All right, now wait a minute. What happened to the 4,500? Minus 4,500 is equal to 0, right? All right, do the math, y'all. So the sum of the forces into Y is equal to what? Well, that 0.6 times 0.75 comes out to be what? 0.6, oh shoot, 0.6 times 0.75 is 0.45 T1 plus 0.799 T1 minus, I tell you what, yeah, I'll go ahead and do that, equal to 0. And so we got sum of the forces into Y is equal to, that adds up to be what? 1.3? Is it 1.3? 0.799 plus 0.45. No, 1.25. I was miscalculating. So this is 1.25 T1 is equal to 4,500. You add 4,500 to both sides, and T1 is equal to what? 3,600 newtons. My Lord, the mercy, you mean to tell me we had to go all the way around that way? Yes. Okay. All right. Now what do we do? So that's T1, but how do we find, what if I ask you to find T2? What is the tension for T2? Right? What's the tension for T2? All right, take our equation, go back right here, and plug in T1. All right, let me see now. Hang on a minute. Take this and plug it in right here, and you'll find T2. Okay? Can you do that if I ask you to? And that'd give you T2. And again, why are we not doing the X? Because they're canceling each other out. Okay? They're canceling each other out. All right? Okay. Any questions about that? That's a good problem. Hint, hint, hint. I might like to stick that one on a test. All right. Okay. All right. Any other questions on here you want me to look at? Now look, number 4 on your worksheet is worked exactly like number 2. Okay. Except there you actually have to find the weight of the mass. Well, you just multiply it times 9.8. Any others on there? Do you want me to look at some of the textbook problems? Or do you want to do another one of these? You want to look at the textbook problem? Chapter 4. Now we did number 1 the other day. And if you can do number 1, you should be able to do number 2. Okay? And number 5. Okay? All right, what about any of these on chapter 4? Any jumping out at you? 11. Okay. Now this is chapter 4 problems. Okay. That other was the worksheet. Okay, this is on page 124 in the textbook. Okay. All right, so we got a hockey puck with a mass of 0.16 kilograms is at rest at the origin on the horizontal frictionless surface of a rink. So we got a rink, we got a hockey puck. Should have time to work this. Okay, we got a hockey puck here. Okay, and it has a mass of what? 0.16 kilograms. Okay, and it's at rest. So its initial velocity is what? 0 meters per second. Is that right? And its initial x is 0 meters. Okay? So it's at the origin. So let's draw our axis here. Of course, that's going to be the x and the y. This is x and that's y. All right? All right. At time t, 0, a player applies a force of 0.25 newtons. So we got a player here. He hits it at time 0. In other words, initially, the force applied, and we can just say FAPP, is 0.25 newtons, right? To the puck, parallel to the x-axis. She continues to apply this force until 2 seconds later. So it goes from time 0 to time 2 seconds. Okay? All right? Applied force. All right. What are the position and speed of the puck at 2 seconds? Okay. All right. Well, the first thing we need to do is the puck accelerating? Or is it at equilibrium? Well, they apply a force, and anytime you apply a force, what happens? Right? Okay? Yeah? All right, so that's Newton's second law, isn't it? So what's missing? All right, whoa, let me back up. So we want to know at A, what is the position and the speed. So we want to know A, we want to know X final and V final. Right? Okay? Well, we're missing something, aren't we? How am I going to find either one of those if I don't know one variable? What is that variable I need? Now, we've got time, we've got initial velocity and initial displacement, we have a force, we have a mass, but we're missing acceleration. But look, y'all, we can find it right here. Right? The acceleration's what? 1.56 meters per second squared. Is that correct? Okay. Now we can find the final displacement. All right, y'all. Remember I told you we weren't going to run off and leave kinematics. How can I find final displacement? What kinematics? One I told you we use a good bit that has displacement in it. Right? Yes? All right, plug everything in. 0 plus 0, because initial velocity is 0, y'all, plus 1/2 times 1.56 meters per second squared times the time of 2 seconds, because that was the delta t. Oops, squared. And so we get a final displacement of what? 3.12 meters? Is that right? That's crazy. All right. So, what is the final velocity? Well, what equation can we use here? Well, what kinematics had final velocity in it? Easy one. Easy one. There's actually probably a couple you could use. The first one. All right, so that's equal to 0 plus, that's a plus, by the way, VI plus AT. Plus what? 1.56 meters per second squared times what? 2 seconds? And we get what? Well, what do you know? 3.12 meters per second. Right? All right, any questions on that? That's a good problem. All right, now let's look at 11b. All right, if the same force is again applied at 5 seconds, what are the position and speed of the puck at time 7 seconds? Okay, so we're missing something here, aren't we? All right. So what happens after 2 seconds? What happens from 2 to 5 seconds? It just slides, doesn't it? Very good. So from 2 seconds to 5 seconds, the puck has constant speed, which means acceleration is equal to 0 meters per second squared, right? All right, so we hit it again. Now let's look at it. It says if the same force is applied again at 5 seconds, so at time equal 5 seconds, we have a what? 0. What was that force? 25? Yeah. 25 Newton force all the way to 7 seconds. T is equal to 7 seconds, right? It is 7, right? Yeah. All right. Okay. All right, so what was the final speed at 2 seconds? Okay, 3.12 meters per second. All right. Would it be right to say that the velocity, the final velocity at 2 seconds would be equal to the initial velocity at 5 seconds? Would it be right to say that? Yes, it would. So the initial velocity at 5 seconds is equal to 3.12 meters per second, right? Okay. Well, where are you going with this? All right. Well, notice it says, what are the position and speed of the puck at 7 seconds? So we want to know what x final is at 7 seconds. Well, it's equal to what? All right, now look. You remember that velocity average is equal to delta x over delta t. And so what would x final be? The change in displacement will be equal to what? 3.12 meters per second times what? 3 seconds? Okay. And that gives us what? Is that right? 9.3, now watch, 9.36 meters from, from time 2 seconds to time 5 seconds. You see what I did there? I'm finding the amount of displacement during that 3-second time interval because it's constant speed. Right? So what is the initial displacement going to be now at time 5 seconds? Well, we went 9.36 for those last three plus 3.12 for the first two. So the x initial should be 12.48 meters, and that's at 5 seconds. Right? Do you see what I did? We already found it for the first 2 seconds, then we got to find it for the next 3 seconds. Well, it had constant velocity there. So you got to add both those displacements together. Now we can do this, can't we? We can say the x final at 7 seconds is equal to 12.48 meters plus, what was the initial velocity at 5 seconds? 3.12 meters per second. And it travels for how long? 2 seconds. 5 to 7 is 2 plus 1/2. We do the same acceleration. That's not going to change. Times 2 seconds squared, and the final displacement is what? 21.48 meters. 21.48 meters. And that's at 7 seconds. And guess what? You use the same equation for final velocity at 7 seconds. So we do what? 3.12 plus 1.56 meters per second squared times 2 seconds. And we get a final velocity, oh shoot, I run out of room, of 6.24 meters per second. All right, all right, let me do this. At 5 seconds is equal to 6.24 meters per second. Okay? Did you get it? Boo, that one was a little tough, wasn't it? You just have to think, y'all. You can't freak out. You got to remember, oh yeah, from 3 to 5 it's from 2 to 5 it's moving with constant speed. Well, I can use that to find my displacement and then go back and plug it into my x final equation after I've added the 2 displacements together, and boom, here we go. Okay? All right.